Potential energy. Potential, well, an object has kinetic energy when it's what? Is it cold? Do you want to shut the window a little?
Is it open?
Yeah.
Don't worry about it. I can live.
We'll shut it down a little bit.
We had this battle yesterday in class. Just crack the window open.
It was just really hot in here this morning. All right. Potential energy. Let's go back to kinetic energy. When does an object have kinetic energy? When it's in motion. All right. When does an object have potential energy?
Is that right?
When it's not in motion, does that mean it automatically has potential energy? Not necessarily. But what does it... So when we're dealing with a different type of energy, it may have it, it may not have it. But potential energy, we like to define it, or I like to define it anyway, as energy due to an object's position. All right. Now, if you took Physics 1, you probably learned about a few different kinds of potential energies. Anybody remember? Gravitational potential energy. All right, well, what we're going to find out is that where there's only one kind of kinetic energy, 1/2 mv squared, that's it, there are many different kinds of potential energy. So there's different kinds. The ones that you normally see within AP Physics, or at least in the mechanics part of AP Physics, are potential energy due to gravity. And the symbol, by the way, is a U, not PE. So I know in first year physics we teach PE, and then we come to AP and it's a U. So we have potential energy due to gravity. We're going to find out that springs have potential energy. And if you took AP Physics C mechanic, E and M, you'd also find out that there's electric potential energy as well. So there's a bunch of different kinds of potential energies. All right. Now, you know there's a formula for potential energy due to gravity, right? And you learned that last year as mgh. Guess what? There's a different formula for potential energy due to a spring. There's another formula for potential energy due to an electric field. Depending upon the spring, whether it's a linear spring, a nonlinear spring, you can have different types of potential energy. So the formulas are ridiculous. So, of course, what do we like to have?
A universal formula.
A generic formula. That always works for potential energy. And that generic formula is going to be the change in potential energy is equal to the negative of the work done by, I'm going to just abbreviate this, CF, where CF stands for conservative force. So what the heck is she talking about here? So what is negative work done by a conservative force? So first of all, we have to talk about what a conservative force is, and then we can figure out where this all comes from, and you'll see why, UG is mgh. All right, so anybody know anything about conservative forces? And this is, by the way, is the work done in changing the object's position from one place to another. Anybody know anything about conservative forces? Well, right away, guess what? G's a gravity's a conservative force. Spring force is a conservative force. Electrostatic force is a conservative force. So conservative forces always have these potential energy functions associated with them. And what makes a force conservative is the work done by a conservative force is independent of the path an object takes. What that means is all that matters is where the object started and where the object ended. And it doesn't matter how you get there. So let's try a little example to see what I'm talking about. And we'll look at Fg and see that this is a conservative force. So we've got 5 people here, so the 3 people on this side of the room are going to do one of my calculations, 2 on that are going to do another calculation. Alright, so we're going to say we have a 2 kilogram mass, and we want to lift this mass 4 meters high. I want you to figure out the work done by gravity in that case. Alright, the other half of the room, you're going to have the harder problem, I'm sorry. We're going to take that same 2 kilogram mass, and we're going to push it up the hill, again, making it end up at 4 meters high, and we'll make this a, we'll do a 3, 4, 5 triangle, so this is 5 meters along here, so I know what that is. So that's about 53 degrees. I want you to figure out the work done by gravity for that one. So in both cases, figure out the work done by gravity.
Wait, so we're doing the ramping.
So yeah, you 2 are doing the ramp, sorry. And then everybody else has got the easier one on the right side.
And we can always use 10 for gravity.
Yeah, use 10 for gravity, keep it simple. You will get no points taken off on the AP exam for using 10. Because the important thing is knowing that you have to use it, more so than having the exact 9.8 value. Can we just go back to FR cosine theta here?
Yes.
Yes, because it's gravity a constant force.
Yes.
We're going to find, though, when you get to your planet, your unit on orbits and so on and so forth, that gravity is not going to be a constant force when you're talking about planets across the solar system and satellites and things like that. But I'm sure you'll get to that later in the year. But for now, we're going to say gravity is a constant force because we're moving something 4 meters and, you know, G's not really changing. All right, so if we go back with our FG, R cosine theta, what are we plugging in for FG here? mg, which would just be 20. What are we plugging in for R? 4. What's the angle between FG pointing down and R going up?
180.
180, so we're going to get a cosine of 180. So how much work does gravity do?
-80.
Negative 80 joules. All right, now if gravity is indeed a conservative force, when I calculate it over here, I should also get negative 80. So let's see. FGR cosine theta. FG is still what value?
MG.
We're mg, which in this case is going to be 20, right? Here's my FG, here's my R. What's the angle between those two things? 90 plus 53, right? So you get the, oh, we forgot R. What's the R? How far am I pushing this thing?
Are you using 5?
5, yep, sure. I mean, there's different ways to calculate it, but we're going to do that. 20 times 5 times the cosine of 90 plus 53. What do you get when you do that? Hopefully, it better be. Oh,
So that's the same thing as just doing sine of 53, right? That's what I did. Or
yeah,
the-
basically what you did then is you looked at the component of gravity that was actually doing the work in this case.
Okay.
So yeah. So that's the same thing. So did you get minus 80?
Yeah, like minus 79.
Yeah, so because 50, it's really, it's like a 53.1 something or other angle, we're rounding it off. So you get minus 80. So gravity is a conservative force. If I took this stapler off the table, lifted it up, put it down, walked over there, put it on the ground, carried it, walked around the room, and ended 1 meter above where I started, gravity does the same exact amount of work as if I just lifted it up 1 meter to begin with. All that matters is where I began and where I ended. So gravity happens to fall into this category of conservative force, so it's going to have a potential energy function associated with it. Springs fall into this category as well, and so do electrostatic force. Example of a non-conservative force. Any ideas? Friction is an example of a non-conservative force. So let's just imagine, so we'll take a look at friction. I think I used that as my little example here. Let's imagine that I had friction. Let's just make up a friction value. We'll say the friction force is 100 newtons, and I'm going to move this 10 meters to the right. How much work would friction do?
1,000.
It would do
Or, yeah.
100 times 10 times the cosine of 180. It would do
Or
how much?
negative 1,000.
Negative 1,000 joules of work. Now, maybe I don't want to push it. So maybe here I am, I want to go from here to the end of that, the end of the desk. And the first time I pushed it straight across, but now I'm going to do this. I'm going to push the box, push the box, push the box. I'm going to zigzag all the way. So when I take my box and I go the 10 meters to get to here, I zigzagged and covered 40 meters to get to that 10 meters. How much work does friction do now? It's still the same 100 newtons, but now the distance that this acted over was what? 40 meters. The angle's still what?
Negative 180.
Because cosine of 180, friction, as soon as I changed directions, what did friction do? It changed direction, and it just keeps opposing my motion. How much work was done by friction now? Minus 4,000 joules. Did I end up in the same exact spot? Did I do different amounts of work? Non-conservative force. So friction will not have a potential energy function associated with it. All right, so why do we care? Because I'm sure that's your next question. So let me just list what conservative forces you will see. In this class, in mechanics, you're going to see gravity and spring forces, non-conservative forces. The classic one, of course, is friction. And going with friction would be, drag force would be a non-conservative force. Any kind of applied force, push, pull, whatever, is a non-conservative force. Like tension, things like that, if they do any work, would be considered non-conservative forces. And again, this is going to come into play when we finally tie all of it together with conservation of energy. All right, so let's go back to this idea of where does this come from? Delta U equals the negative of the work done by a conservative force. Because we're going to be using this to come up with all of our potential energy, basically it's a way to come up with a formula for potential energy. So let's take a look, and now we'll do things. We already know the formula for potential energy is, from gravity, is mgh, as long as we're near the surface of the Earth, so we're going to work with that. All right, so here's our mass. We're going to keep it generic. We're going to lift this mass a height h. Okay, and we're going to lift it at a constant velocity. How many forces are acting on the object if we lift this at a constant velocity?
2.
2. Figure out the work done by each of them. So there's going to be an applied force, and there's going to be gravity. So how much work would the applied force do?
MGH.
So it's going to be the F of mg, the distance of h, and a cosine of 0. How much work would gravity do?
Negative MGH.
It's going to have a force of mg, a height of h, and a cosine of
Negative 180. Or no, sorry, 180.
Cosine of 180, so
Which is
that
negative
gives me a negative mgh. What was the net work done on this thing?
0.
0, so did its kinetic energy change at all?
No.
No. However, because the thing is now hovering or being held h above the ground, gravity has the potential to do work if I let this thing go back to where it came from. I've changed its position, and because of that, this now has the ability to do work. And that's why some people say that potential energy is not energy. It's not energy. It doesn't have any energy until I let it go and let gravity actually do the work. Right now, it's just what they like to call a stored energy or something. It's there, and if I let this mass fall back, then the energy will show itself because gravity is going to do work and give it kinetic energy, but it's not really energy in its own right. But it has the potential to do some work. So if I let this go, how much work will gravity do if I let this go? Well, let's think about it. Now I have this gravity pointing down, so it's going to be F, the mg. It's going to move a distance of what? H. And what's the angle this time?
0.
It's cosine of 0 this time. So the work that gravity does is equal to mgh. And that, what we're saying, is the potential energy that it has. Because if I let it go, it can do that much work. And it's really a delta U. It's change in potential energy because I'm the one who decided to lift it from the ground to somewhere else. You know, because basically it's like you chose your reference point to be the ground. So gravity has the ability to do that much work if I let it go. So what happened? I changed the mass's position, and that's what potential energy depends on, a change in position. Because I changed its position, it has the ability to do some work. How much work could it do if I let it go back to where it came from? It could do mgh of work. So we say that's how much energy it has stored up. The amount of work that it can do if I let it go. Does that make sense?
Yeah.
All right, so let's go back and see where this equation comes from. All right, so this delta U, here it is, mgh. Well, that's equal to the work I did to lift it up there, isn't it? Or it's equal to the negative of what? The negative of the work that gravity did when I moved it up there. And that's why it's listed as the negative of the work done by the conservative force when you moved it from one place to another. So that's where that equation comes from. So in this case, delta U equals mgh, which happens to equal WA, the work done by the applied force when I moved it, which happens to equal the negative of the work done by gravity when I moved it. So basically, I moved it, I changed its position, gravity fought me on it, and now if I let go, it's going to go back to where it came from, and gravity's going to do all that work to get it back to where it came from, and it's going to basically then get kinetic energy from that. So this is our generic formula for the potential energy function. And you can use that to figure out the potential energy associated with anything. So let's take a look, because remember I circled a formula earlier today? And I said this is going to come back to us with potential energy. Let's go back to that. So here's a spring. A spring is a conservative force. So it's going to have potential energy associated with it. So let's just pretend I have a mass attached to the spring, and I'm going to move that a distance x. And this happens to be a linear spring, so it's going to follow Hooke's law. Alrighty? Now, am I going to change the position of this mass that's attached to this spring?
Yeah.
Yep, so the spring force, which is a conservative force, when I moved it to the right, the spring force does some work. Because of this, if I sit here and hold this thing to the right, it's going to be stretched out, does the spring now have the ability to do some work if I let go? I do. So we're going to say the spring has potential energy stored in it. Because when I drag this and hold this at a position X, that spring doesn't want to be stretched. And if I let that go, the spring's going to go back to where it came from. So the spring has potential energy. Well, gee, how can I figure out how much potential energy that spring has? Well, I could say the change in potential energy of the spring is the negative of the work done by, well, we'll put in conservative force. What is the conservative force in this case? The spring itself, right? All right, so let's figure out how much work this spring does when we stretch this thing a distance x. So when stretching it at x, we want to figure out the work done by the spring. So what comes into play again? F dot dr. Why can't we write down Fr cosine theta? Why can't we write down Fr cos, just not, get rid of the integral. Why do we have to go with the integral form this time? Because is the spring force a constant force? No. So we have to start with this. We're going to get rid of the dot and write Fs cosine theta dr. When I'm moving this to the right, what direction is the spring force? To the left, because we know that spring force fights the chain, you know, the elongation or the compression. So I can plug into this. The spring force is going to be Kx. And what's the angle going to be? 180. And again, do we care if it's dr? No, we're going to just call it dx. And we're going to go from 0 to x. So what do I get for the work done by the spring when I stretched it? So the work done by the spring is going to be negative kx squared over 2 from 0 to x, which is just, obviously, negative kx squared over 2. Well, now if I wanted to figure out the potential energy associated with that spring, it's negative kx squared over 2. And what do I get for the spring potential energy? What we circled before, that kx squared over 2. Because the work that the spring does is the potential energy that it has. Because if I let this go, the spring now has the ability to do that much work. So this is the equation for the potential energy of a linear spring. What if the spring weren't linear?
Angle would change.
Not that the angle is going to change, but will it follow kx anymore?
Could be like kx squared.
Could be a kx squared, kx to the half, kx, whatever they give you, and then you can find the potential energy of that spring. Yeah.
So if there was a free response question and it was about a linear spring and like the first part was find the potential energy of the spring, do you have to go through all this?
I don't think you do because I believe they give you that on the AP sheet. But what they probably would end up doing is some kind of, like the question that we just did, you now had to then figure, well, you could do it from a, I guess it's from a conservation of energy approach. So the question we just did in the end is you had done work, or the spring had done work, I think they phrased it. And then because of that, the spring now had potential energy, and then you can use that in the, you know, but you had to actually come up with the expression for it in this problem in order to calculate the work done. And then you have to realize that that work that you did in compressing the spring did negative work and therefore has potential energy and all that other good stuff. But to use kx squared, I think that's right on the sheet. I think it says u sub s is equal to 1/2 kx squared. Yeah.
What would a nonlinear spring be?
What's that?
What would a nonlinear spring be?
They're going to just give you a different function.
Okay.
So they're going to just say it varies with some other power of x. So it's going to vary with x. So like the problem we did, just, when you guys came in, we had a spring on the back that varied with ax squared.
Oh, okay.
So they would have some other value of x, and they would have to either tell you it or give you the data to figure it out or something. They're not going to be able to deal with that. All right, so any conservative force has potential energy associated with it. You can come up with the potential energy equation by just figuring out the negative of the work done in moving that or changing the position of that object with that conservative force acting on it. And when it comes to springs, it just happens to be kx squared. Now the last little bit about potential energy is they like to use these potential energy graphs. But let's go back to this whole idea that delta U is minus the work done by a conservative force, because there's going to be another way to look at potential energy and so on. So if we go with this, we can say delta U is equal to minus, what can I plug in for work done by a conservative force? I can plug in the integral of F conservative force dot dr, yes? And if the delta U is equal to the sum of all the drs, then what would just a little tiny change in potential energy be equal to? Would I have to sum all these things up? So in other words, I'm saying to get the total delta U, I have to integrate and add up all the little drs. If all I want is the infinitely small change, I can completely drop the integral, because I'm just looking at one infinitely small change. I don't need to add them all up. Alrighty? And we're going to assume that the angle is going to be, in the right direction, so that this conservative force is, going or acting against position and so on. So another way that you can write this is a conservative force is equal to the negative of the derivative of the potential energy that it has with respect to R. So basically, all conservative forces have potential energy functions associated with them. And again, you can either think of the delta U as being the integral of the force, or you could think of it as the force being the derivative of the potential energy. Does that make sense? So they kind of go hand in hand. So what that brings us to is these class of problems, and again, R could also be X, right? So it's just position. This brings us to this class of problems that don't show up all that often, but do show up every now and then, where they give you these graphs of potential energy functions. So they'll be like, oh, here's a graph of potential energy with respect to position. And then they'll start asking you lots of questions about this graph. And we're going to do some of these because I brought them. Alrighty.
Would that be like in the multiple choice, like use the following graph to answer?
Yeah, but it'll also be full-blown problems. So I brought 2 full-blown problems with potential energy functions and graphs. Alright, so key things you want to know about these graphs. The derivative of this graph is equal to what? Or the negative of the derivative of this graph is equal to the force. Okay? Which means what of this graph is equal to force? The derivative is really just a fancy way of saying the slope. So the slope is equal to the force. Tell me about the slope at this point and that point. Well, right at this peak and right at that, trough there. How much slope do I? So the slope up here is 0. Which means, what's the force? 0, which means I am in what? these what we would call equilibrium points. So they often ask about when the object's in equilibrium and so on. The other thing that I like to do with these graphs is talk about stable equilibrium and non-stable equilibrium. So if you had a certain total energy, so again, thinking that this has got numbers on it, and let's say the total energy that you could have in your object is this much. So we'll say this is the total energy. And really the best way to do this is to just do some problems with this. That's the total energy. And that total energy is always going to be made up between potential and kinetic. Because when I have something that has potential and I let the object do what it wants to do, that energy becomes what when I let it go? What kind of energy? It becomes kinetic. So it's always going to be a trade-off. The object's going to have this stored energy, and if I let it change its position, then it's going to go back to kinetic energy. So what would happen if I had an object with this much total energy is that if I let it go here with all this potential energy, it's going to go back to where it wants to go, and it's going to gain kinetic energy. And it would have its maximum kinetic energy here. Then it would keep moving x, and as it moved along, what happens to its kinetic energy and what happens to its potential? As I move this way, potential would go back up and kinetic energy would go back down. Could it ever get any higher than that point? If that's the total energy it has, to go higher than this point would require more energy. So at this point, the object would stop, turn around, and start to
Go back.
come back and pass through equilibrium and then go back this way, get to this highest point, turn around, and come back. This is what they call a point of stable equilibrium. Think of like a pendulum swinging back and forth would be an example of this. The object is going to just oscillate around that point. This would be a point of unstable equilibrium. Because if I had an object here and it started to convert its, get rid of its potential and go to kinetic, it's never coming back there, is it? It's going to just go off and do whatever.
So would that be like the projectile at the top of its arc, or?
Yeah, that would be a projectile like at the top of it. It's never coming back to that point. This would be a point of unstable equilibrium. So they like to ask kind of about those things. I find that with these potential energy functions, the best thing to do is to do problems with them because they're kind of like vague and difficult to work with other than to actually talk about them. So what I'm going to do is I'm going to give out multiple choice. What time does lunch officially start? Lunch officially starts at 12:10, so we'll spend 10 minutes doing, there's only 6 multiple choice, so we'll try to do these multiple choice questions.